I'm happy to be here to introduce our efforts on optimizing sparse gem on Nvidia GPU. And this is the outline of my presentation today. I will start with a brief introduction on the work backgrounds to make sure that we are all on the same page. And sparsity is a very important feature in many scientific and AI workloads. For example, simulations, linear algebras, and machine learning models. And many recent studies report that sparse computation often becomes a major performance bottleneck. For example, sparse computation can take up over 80% of the total execution time when training a graph neural networks. And in large language model, when we grow the parameter size, model pruning introduces sparsity to save compute. This again relies heavily on the sparse computation. So across the board, from scientific computing to AI, a core operation keeps growing up, the sparse matrix multiplication, or SpMM for short. I will talk about how to optimize this specific kernel today. We know that GPU are the main engine for compute-heavy workloads. On an Nvidia GPU, there are two types of compute units. One is CUDA cores. These are general-purpose units. On an H100, they can reach about 67 teraflops in FP32. Another is Tensor Cores, which are specialized for matrix multiplications. They can go all the way up to 89 teraflops using TF32. This is nearly 15 times performance boost just by switching to Tensor Core. So obviously, Tensor Core brings massive speed up for matrix operations. However, SpMM has a mismatch structure for Tensor Core. Here we have two, for example, here we have two input matrices. The left one is usually highly sparse and irregular, while the right one is dense and well structured. This input combination makes it hard to fully use Tensor Core since Tensor Core prefer regular and dense patterns. Because of this, lots of existing work focuses on using CUDA core to speed up the SpMM kernel. But things changed a little bit after 2023. TCGNN is the first one to make it possible to map the irregular SpMM onto regular Tensor Core hardware efficiently. Since then, more and more research studies has been looking into how to unleash Tensor Core power for SpMM kernel. Another thing we need to pay attention to is Nvidia's Hopper architecture, which is now one of the most widely used advanced GPU platform. What makes Hopper special is fully asynchronous design. At hardware level, it introduced WGMM to invoke Tensor Core asynchronous and use a new hardware unit called Tensor Memory Accelerator, or TMA for short, to decouple the data loading from computation. And it requires a synchronization between the data loading and compute, which is handled by the memory barrier. And this also brings a new software programming model. On Hopper, a high-performance gem can be achieved using the world's specialized persistent kernel. You can think about it as a producer, some consumer pattern. Some work group act as a producer. They load the tiles data using the TMA, and others are consumer. They do the actual computation using the WGMMA. This pattern overlaps memory load and compute, which helps get the most out of Tensor Core. And CTA persistent kernel launch a fixed number of CTAs, usually matching the number of XM, so they stay resident and avoid the launch overhead. Another feature is the multi-stage pipelining. It overlaps the different stages of the pipeline, for example, storing the results while already we can start the next stage for the compute. This boosts the overall throughput. However, so far, most of the existing study has been on the dense gem. It has not effectively used for the sparse SpMM yet. And that's why I'm here today. I will talk about what the challenge it is To map sparse computation onto Tensor Core, TCGNN introduced a smart graph translation technique. The idea is to compress a sparse matrix onto several compact blocks. They call it TCO block. And each block is carefully shaped to match the size of Tensor Core operation. This makes it possible to map the irregular sparse workload onto the irregular hardware of Tensor Core. TCGNN did a great job. And they showed that the Tensor Core can be used for sparse computation, but there is still a big problem. Even with this transformation, data loading becomes the new bottleneck. And it is even worse in Hopper because the new hardware, the compute throughput is much higher. And this figure shows the bottleneck breakdown from our experiment on multiple data sets. We found that the data loading alone takes over 80% of the total execution time. This is mainly due to the two things. One is from the efficient sparse format, and another is from the naive async loading for the dense matrix data. As a result, Tensor Cores, they hungry most of the time. They are just waiting for someone to feed the data. So while the compute part is fast, the kernel as a whole remains inefficient. We also find another big challenges in SpMM is workload imbalance. First, the top one is the output balancing techniques. Here, each CTA is assigned to compute all TCO blocks in a single output load window. For sure, this makes the output nicely balanced. Every CTA only writes to one load window, but the problem is on the input side. Different loads can have very different numbers of TCO blocks. That means some CTA will have much more work than others. That leads to the poor load imbalance, wasting the XM resource. Now let's take a look at the input balances, which is introduced in DTC SpMM. This time, each CTA is given the same number of TCO blocks, so the input is evenly balanced, but now the output becomes maxed. When one load window has lots of TCO blocks, then multiple CTA had to merge their result, which require an automated operation. And these automated operations are very expensive for GPU, with slow finish time. And when a CTA writes to multiple loads, the output cost varies between CTA, which again causes the imbalance. Due to the irregular nature of the sparse data, if you only balance the input or only the output, the other side becomes unbalanced. So we want to avoid those expensive operations. So ideally, we want a new partitioning scheme that could balance both the input and output and keeps the word units cost enough to avoid the clocking load window bottling. That's exactly what we aim to do, and I will show you how in a moment. Next, we'll move to our system design to understand how we unleash the power of Hopper. To address this challenge, we propose our solution, which is SpMM. SpMM brings major improvement to sparse matrix multiplication through three key innovations. First, we use a bitwise level format to compress the sparse matrix. This gives us a correct memory access and the band conflict-free decoding, which improves the memory loading efficiency. Second, we design a work-level asynchronous pipeline, which fully decouple the data loading from the computation. And this overlap leads to a higher compute throughput. The third one is that we build a persistent and balanced kernel which achieves the co-balanced input and output workload, solving the imbalance problem that we saw earlier. Together, these three techniques significantly boost the overall performance. Let's now take a closer look at how we handle the sparse matrix data used in MMA operation on Tensor Core. Sparse matrix is usually stored in a sparse format like CXR, but that means we have two steps to handle the data. The first is we need to load the sparse matrix from the global memory in a complex format, and then decode it into a dense fragment format used by MMA. During the loading, we want to reduce data size and minimize the load instruction. And during the decoding stage, we want to avoid band conflicts in shared memory. So we introduce a new data format called BMAC, short for bitwise complex matrix. As shown in the figure, we use a new data structure called load window offset to mark where each load window begins in the sparse matrix. Then we can represent each element in the sparse matrix either 0 or 1 with just 1 bit. So in a full system by A sparse matrix, it becomes a 128-bit BMAC. This actually perfectly fit into the 32-bit integers, which means that we can load all of this at once using a vectorized LDGX-TX instruction. It is fast, efficient, and correct. Next, we need to map the BMAC into a fragment for MMA. Other work such as ATC, SpMM use the low major tiling or chrome major tiling, but those often cause the band conflicts, as flags have to access memory in conflicting ways. So we propose a hybrid tiling strategies to avoid conflicts. We split the sparse matrix into 4 8x3 blocks. This alignment avoids the slow and conflict memory access. And actually, this technique is kind of similar to the Switzerland. And next, let's look at how we overlap the data loading with computation. In Voltrix, we adopt a word specialized producer-consumer model. Here's the idea. Within each CTA, we divide the word groups into 2 groups. One is for producer, so which load data from the global memory to shared memory, and consumer, which fetch the data from shared memory to the compute on Tensor Core. And this creates an interval pipeline where the shared memory acts as the buffer between these 2 agents. As shown in the figure, the producer handles both the data loading for the sparse matrix and dense matrix. For the sparse, we use our complex BMAC format from introduced in the earlier. So one vectorized instruction can move the entire 128-bit BMAC into the shared memory. For the dense matrix, to load this value efficiently, we actually use the asynchronous TMA instruction. TMA has 2 key benefits. It only launches 1 instruction to load a type of data. In fact, that means A flags can load all of the dense data for a CTA. And we use the M barrier to coordinate the pipeline between the producer and consumer. This creates a ping-pong pipeline between the loading and compute. This helps us hide even more data loading latency and makes better use of Tensor Core. And now let's look at the final part of our design. How we achieve software-hardware balance and input-output cobalance in a persistent kernel. Voltrix SpMM uses a persistent kernel with a fixed number of CTA, which is equal to the number of XMs. This has 2 big benefits. It aligns software and hardware, so every XM is active all the time. The kernel stays persistent, running in a loop until all the sparse data are processed, which avoids kernel relaunch overhead. And different from existing Voltrix use a cobalance partitioning strategies. On the input side, we partition the sparse data at the low windows level, keeping the data clean and contiguous, so no automated operation is required. On the output side, we slice the dense result matrix by its column, so each CTA gets a fair share of output rows. This partitioning matches perfectly with our XM-aligned design and let the persistent kernel run until everything is done. Besides this, we build a lightweight scheduler inside our kernel to split all the tasks evenly across the number of XM using a word-level granularity. And let me walk you through an evaluation of the Voltrix SpMM. Voltrix is a pure CUDA library, about 5,000 lines of code with no third-party dependencies. Specifically, we use inline pretext to access Hopper-specific hardware feature, for example, the MMA, TMA, and M barrier to get the most out of the architecture. And Voltrix SpMM is integrated with PyTorch 2.5 and can be used from both Python and C++ using standard data format, for example, CXR. And our work went through the artifact evaluation, and we open source the code on GitHub to encourage community use and collaboration. And let me quickly walk you through our experimental setup. All our experiments run on Nvidia Hopper H100 PCIe GPU. And those are the related data sets and baseline we use in the paper. I just wanted to highlight one thing that we compare Voltrix SpMM to both the CUDA cores base and Tensor Cores baseline. And this is the kernel performance on graph dataset. Voltrix SpMM consistently outperforms all the baselines across nearly all the datasets. On average, we achieve a 2.5 times speed up over Sparse, and from 1.7 to 35.5 times speed up over other SpMM implementation. The performance advantages becomes even more noticeable as the dimension of the dense matrix increases. And now let's take a look at the results on the Sparse dataset. Again, Voltrix SpMM leads across all the board, achieving an average speed up of 2.5 times over Sparse. Just like on graph dataset, we see that our performance scale with the matrix dimension. We can also see that DTC SpMM is still 11% slower than the CUDA core-based log, and TCGNN falls behind by 70%. This is interesting. Well, most of the existing Tensor Core-based method cannot be the CUDA core-based implementation, but Voltrix SpMM makes it possible, achieving 1.6 speed up over log and becoming the first Tensor Core-based SpMM implementation to consistently outperform the best CUDA core-based method. And this result really showcase that our design unblocks the full potential of Tensor Core on real and diverse sparse workloads. I mean, this pretty much I have today, and any question is appreciated. Thank you.